Assalamu alaikum. Yes, in previous lecture we discussed the limits of trigonometric functions, and we discussed one of the standard limit, that is limit x tends to 0 sin x upon x is 1. Now today we will discuss another limits. First one is prove that limit x tends to 0 1 minus cos x upon x is 0. Now here when we substitute in this cos x 1 minus cos x upon x as x equals to 0, it is 1 minus cos 0 upon 0. Cos 0 is 1, it is 1 minus 1, so 1 minus 1 is 0, so it is 0 by 0 form, which implies that indeterminate form. So this means that we cannot substitute the value of x directly in this function. Also we know that 1 minus cos x is twice sin square x by 2, which implies that 1 minus cos x upon x is twice sin square x by 2 upon x. Now this sin square can be written as sin x into sin x, and this 2 in the numerator can be written as x by 2. Now taking limits as x tends to 0 on both sides, it is limit x tends to 0. 1 minus cos x upon x is limit x tends to 0. Sin x upon 2 upon x by 2 into sin x by 2. The product of the limit equals to the limit of the products, which implies that limit x tends to 0 sin x by 2 upon x by 2 into limit x tends to 0 sin x by 2. Now when x tends to 0, x by 2 tends to 0. So this means that here this x tends to 0 can be written as limit x by 2 tends to 0, because x tends to 0 is equivalent to x by 2 tends to 0. Also, limit x tends to 0 into sin 0 by 2, it is simply sin 0 by 2, that is sin 0, which is 0. So it is 0 into this limit x by 2 tends to 0 sin x by 2 upon x by 2. Now this, when limit, that is x, angle and the denominator are same, this means that this standard limit is 1, which implies that limit x by 2 tends to 0 sin x by 2 upon x by 2 is simply 1. This means that 1 into 0 is 0, hence the value of this limit is 0. Now another one is limit x tends to 0 sin ax upon bx. Now when we substitute x equals to 0 in this function, it is simply sin a0 upon b0, which is sin 0 by 0. Sin 0 is 0, which implies that 0 by 0 form. So we have to firstly solve this very function. Now here limit x tends to 0 sin ax upon bx can be written as a by b limit x tends to 0 sin ax upon ax, because by taking b out from this limit, because it is constant, and multiplying and dividing by a, that is a by b limit x tends to 0 sin ax upon ax, which can be written as ax tends to 0, because when ax tends to 0 implies that ax tends to 0, so it is ax limit ax tends to 0 sin ax upon ax, that is a by b. Now this is standard limit and its value is 1, which implies that a by b into 1, that is a by b, so its value is a by b. Now we will solve this exercise 13.1, and question number second is prove that limit x tends to pi x minus 27 upon pi. We have to find its limit. Now x minus 22 by 7 is simply a polynomial, so its limit at a point is simply replacing x by pi, that is pi minus 22 by 7. Here this is not equals to 0, because remember this thing, that the value of pi is not equals to 22 by 7, because 22 by 7 is the approximate value of pi. So its value is simply pi minus 22 by 7. Now the fourth one is limit x tends to 4x plus 3 upon x minus 2. This is rational function. For rational function, we firstly substitute the value of the limit in the given polynomial in the given fraction, which implies that it is limit x upon limit x tends to 4, 4x plus 3 upon limit x tends to 4, x minus 2. Because for denominator, for this the denominator at x equals to 4 is not equals to 0. So we can break the limit, which is simply putting the value, it is simply 19 upon 2, because denominator of this fraction or rational function is not equals to 0 at x equals to 4. Now the sixth one is limit x tends to 0, x plus 1 raised to power 5 minus 1 upon x. We have to find its limit. Now when we substitute the value of in this, it is 0 plus 1 raised to power 5 minus 1 upon 0, that is 1 minus 1 upon 0, that is 0 by 0 form. So it is indeterminate form. Now here this x plus 5 can be written as, by breaking the power, it is x5 plus 5x4 plus so on to 5x plus 1. Now this minus 1 upon x. Now this 1 and 1 cancels, we simply get x raised to power 5 plus 5x raised to power 4 plus so on to 5x. Now taking this x common and cancelling with this denominator, we simply get x4 plus 5x cube plus so on to 5, because the constant term is only 5. The limit of this, it is a polynomial, its limit is by replacing x by 0, that is simply 5, because every term except the last term, that is 5, contains variable x, that is why its value is simply 5. Now the seventh one is 3x square minus x upon 10 upon x square minus 4. Now when we let x tends to 2 in this, denominator becomes 0. So this means that we will firstly check. Now 3x square minus x minus 10 can be written as 3x square minus 6x plus 5x minus 10 by breaking the middle or by splitting the middle term. That is 3x into x minus 2 plus 5 into x minus 2 upon x minus 2 into x plus 2, because x square minus 4 is x square minus 2 square, and using a square minus b square, which is a minus b into a plus b. So here we will have this x minus 2 common. So cancelling this, we simply get 3x plus 5 upon x plus 2. So it is a rational function. Both the denominator and the numerator does not vanish at x equals to 2. So this means that we have to replace, or the limit of this is simply replacing x by x equals to 2. So it is 3 into 2 plus 5 upon 2 plus 2, which is simply 11 by 44. 11 by 4. The question number 11 is limit x tends to 1, ax square plus bx plus c upon cx square plus bx plus a, provided a plus b plus c is not equals to 0. Now when we substitute x equals to 1 in the given, we simply get a plus b plus c in the numerator as well as in denominator. But it is given that x a plus b plus c is not equals to 0, which implies that x equals to 1 is not a 0 of this polynomial. Hence we can replace simply x by 1 in the given rational function, which is a plus b plus c upon c plus b plus a, that is simply 1. Because also remember that we can cancel only the non-zero same numerators and denominators. But if numerator and denominator equals to 0, so this means that we cannot not cancel, because 0 by 0 is indeterminate form. So inshallah in tomorrow's video lecture we will continue with this very exercise. So thank you.